using the forces method to determine the efforts in a statically indefinable system due to the temperature effects on it. This is article number 3.10 of the book Mechanical Systems Calculations of the Marine Facilities. If we have to find the support reactions in the statically indefinable system, we can use the canonical equations of the force method. For example, like they indicated on the slide. And these canonical equations, the system of the canonical equations of n canonical equations with the unknown n variables. Each of the equations correspond to the deformation compatibility rule when we decided the statically indefinable system. The physical sense of each of the canonical equation is, for example, the first one. This is the displacement. The first element is the displacement of in the first direction of the cutoff link when doing the main system of the assigned statically indefinable system. The main system is statically definable, and to find the reactions instead of the cutoff links of statically indefinable system, we use the canonical equations. The first summand, for example, in the first equation of the canonical system of the canonical equations of the force method is the product of the displacement under unit force applied in the first direction and the displacement in the first direction. The second factor in the first summand is the magnitude of the force subject to find. So combining all displacement and direction of all forces acting on the mechanical system, the forces x1, x2, etc., xn are subject to find unknown variables, and the displacement impacted by this set of forces, and counting the displacement under the external load, we have the equation of the equivalence of the total displacement to zero as we have statically indefinable system, and we assume that the displacement of the support is zero. So as well, for the direction of the second cutoff link of the mechanical system when doing the system, the main system statically definable of the assigned system, and etc. And we have n canonical equations in the system of canonical equations of the force method. The peculiarity of this approach for determination of the system statically indefinable under action of the temperature effect is that the free summands in the canonical equation of the force method is the displacement under the action of the temperature action. The index T indicates that this is displacement under action under temperature action on the mechanical system. Okay, and the important to use the canonical equations, we have to find the factors in summands. Factors is displacement under the action of unit forces. This is not a big deal, and it is the same, by the way, as the determination of the unit displacement as the lowercase delta letter with indexes 1, 1, 1, 2, etc., and 1, I, 1, etc. The first index indicates the direction of the definite one displacement. The second one indicates the number of force and the impact of which we have the displacement in the product together. We have the displacement in the direction we indicate I 1, 2, etc., up to n displacement. And we have to find first these factors delta lowercase, the set of displacement and action of the unit forces, displacements in all direction instead of the cut of links when doing the main system out of the assigned statically indefinable system. And besides, we have to find the independent summon, that is the free terms of the canonical equation on the force method, is about to find the factors of the magnitudes of the forces subject to find. The approach to find this delta log case factors is the same as usually we consider when determining the support reactions of statically indefinable system. And how to find the free terms, independent summons, independent on the sought support reaction summons of the canonical equations of the force method. So first of all, let's please consider the small segment of the rod and the action of the temperature difference. So this is transverse section of the rod. This is a plane of the rod from the another one direction. And this small piece of rod is embedded by the left side. And it has the length. The length is the increment of the abscissa dx. And this small piece of rod, the increment of rod, experiences the temperature difference. On the other side, it has the temperature T2, on the another side T1. So due to linear distribution of the temperature, we have the distribution inside of the transverse section, any transverse section of the rod. So what is the deformations of this segment, the segment of the beam of rod or any other element of the mechanical system? As the upper fibers of the rod heated for the temperature T2, so we have the deformation of the upper fibers of the rod as a product alpha by T2 temperature of heat in the upper side of the rod, and the product by the increment size dx. The alpha is a factor or coefficient of the linear expansion of the elastic material and direction of the temperature. This depends on the what kind of the elastic material we consider. And for the lower fibers heated by the temperature T1, accordingly the expansion is the product alpha by T1 by the length of the increment dx. And as well, we have in the midline of this one trapezoid, or the midline of the transverse section of this segment of the beam, we have the expansion of the beam by alpha, product by T0, product by dx. T0, we assume that we have linear distribution of the temperature inside of the cut the decrement of the definite one beam heated by one temperature one side and another one temperature another side. So what is the change? This is epsilon. Epsilon indicates the linear deformation at the action of the temperature. The epsilon equal to per unit of the length of this element, epsilon equivalent to the product of the alpha coefficient of the linear expansion by the temperature of the midline of this trapezoid. This is a middle temperature, as we can find, as assuming the linear distribution of temperature inside of this one segment of the beam. The middle temperature on the midline of the section, transverse section of the beam, is just a fraction in numerator T1 plus T2 is the temperatures divided by 2. Temperatures on two sides of the beam divided by 2. This is temperature of the midline. And deformation of this segment of the length dx is epsilon product by dx, and so the alpha is coefficient of linear expansion at the action of the temperature, product by the fraction of the O by the middle temperature of the midline of the section, and product by the length of the increment of length of this beam dx. Besides the section, transverse section of the increment dx of the beam experiences the bending, the rotation to the angle phi. So the small angle d phi, as we consider the rotation of the small sized beam of the length dx, considering the embedding of the left one side of the beam. So the left one side do not move, and moves only the right one side due to the difference of the temperatures on the upper side of the beam and the lower one side of the beam. And the increment of the angle of the rotation of the section equal to the product of alpha coefficient of the linear expansion of the material of the beam, product by the fraction in the nominator. Numerator, we have the difference of the temperatures on sides of the beam, T1 minus T2, and we divided by the height of the beam, h. It's height of the beam and product by dx. So we can find the linear deformation. This is product of epsilon by dx. Epsilon is the product of the coefficient of linear expansion by the temperature of the midline of the beam. And as well, we have the angular deformation. This product of the coefficient of linear expansion by the difference of the temperatures on the lower and upper sides of the beam divided by h, and the product by dx, the length of the beam. The more integral for the displacement and action of temperature has their form. The displacement and action of temperature equal to the integral of total of the moments, product of the moment of unit force in the direction, if we consider a definite one, I direction, product under the sigma sign, the total product of the moment mi of unit force in the direction of the sought displacement of the assigned point in the assigned point of the displacement, product by the angular deformation plus integral of total of the longitudinal forces acting in the element of the mechanical system. This is a total by the elements of the mechanical system. This is the first total and second one total, and the product here under the sigma sign by the linear deformation equivalent to the epsilon by dx, and epsilon is equal to the coefficient of the linear expansion and action of the temperature, and the product by the middle temperature of the heated beam, that is the middle by the section of beam, considering linear distribution as a total of temperatures on two sides of beam divided by 2. Okay, and after mathematical transformations, we can consider that we can separate the total, and we can find separately on the bending moment products by dx. So we can derive the product of the coefficient of linear deformation by the difference of the temperatures on two sides of the beam cause the bending temperature impact of the bending of the beam divided by h, the height of the beam, and the product by separately considered integral, and the integrand is the product of the bending moment on the action of the unit force in the direction we have to find in which we have to find the displacement, and product by dx. And on the second, we have the total of derived out of the integral, the product of the coefficient of linear expansion of the material of the beam by the middle temperature acting in the middle line of the beam. Middle temperature is the T1 plus T2 divided by 2. And in the integrand, we have just the product of the longitudinal force by the length of the increment of the length of the element of mechanical system. And the totals are for each of the mechanical systems. That is the total of all mechanical system elements, these formulas. And considering that the integral of the bending moment diagram by the increment of the length of the element mechanical system dx equals to the area of the diagram of the bending moment at the action of the unit force in the direction we sought for the displacement determination on the action of the temperature. And consider we can substitute this integral by the area of the diagram of the bending moment and action of unit forces in sought direction of displacement. And the integral of product of longitudinal force by dx is the area of the diagram of the longitudinal force. We can consider separate, and that is the way how to find the displacement using Mohr integral, using the areas of the diagrams of the bending moment and action of unit force, and using the diagram of the longitudinal forces and the action of the unit force on the mechanical system to the point of which we look for the displacement in the direction in which we look for the displacement. Okay, so let's go to the exercise. Assign system is statically two-time indefinable, as we have 5 unknowns, is 3 unknown support reactions in the point A, is 2 components of the resultant force applied in the point A and the bending moment in the point A of the support, the bending here. And in the fixed hinge in the point B, we have 2 links. So we have 5 unknowns and we have only 3 equations of balance. So this is 2 times statically indefinable system. We first have to substitute this assigned system by the main system statically definable of the same external load, and instead of the links, for example, we can cut off the links in the support B, both links here we can cut off, and we substitute by the forces x1 and x2 subject to find action instead of the links in the point B. The sizes of the frame are the h 2 meters, the width is 2 meters, and this frame elements, the vertical element, the horizontal element, are of the same rigid characteristic of the rigidity of the elastic modulus and the moment of the inertia of the transverse section. And the temperature impacting on the frame is outside -5 degrees Celsius and inside is 15 degrees Celsius. This is 2 temperatures acting on other sides of both 2 beams within the considered frame. The transverse section of the considered frame is consists of two channels. One, the channel we assume of number 20. Number 20 is a channel with a height of 20 centimeter. It is of the directory, has standard characteristics of the moment of inertia of the transverse section. This is required to find the characteristic of the elasticity and rigidity of the rods within the frame. So this the moment of the inertia relative to horizontal axis of the transverse section is 2 by 1520 and equal to 3040 centimeter powered by 4. The elasticity moment is 2.1 is carbon steel multiplied 10 powered by 5 megapascal, and the H in the international system of dimensions is in general for the channel number 20 the H is 20 centimeter, but it is 0.2 meter in the international system of units as well. For carbon steel, we have the coefficient of linear temperature expansion as 12 product by 10 powered minus 6 per 1 degree Celsius. And the temperatures assigned inside the mechanical system is 15 degree and outside is minus 5 degree. So the bending rigidity is, we multiply the elasticity modulus by the moment of the inertia of this channels to welded together in the points, and the rigidity characteristic is 6.384 multiplied by 10 powered 6 Newton by square meter. So this characteristic of the assigned mechanical system statically definable, we had to find the forces applied to the point B. Exactly, if we have that, we can use the balance equations in the after to find the reaction components in the point A of two components of the force resultant in the point A and the bending moment in the point A. Okay, first of all, we have to use, as we have two unknown variables, so we have to have two canonical equations of the force method. These two canonical equations force method, it consists of three summands each. The first summand is the displacement in the force direction and direction of the force applied in the force direction plus the displacement is the same one force direction. The solve first equation of the displacement in the force direction and the force applied in the second direction, and the free summand is the displacement force direction and direction of the temperature have to be equal to 0. The second canonical equation is the displacement. What this is the directions. The displacement in the second direction and direction of the force applied in the first direction due to deformation of the general frame, plus the displacement in the second direction the same, but in the direction of applied of the force in the second direction, plus the free term is displacement in the second direction and direction of the temperature on the mechanical system. So to find these factors and low case deltas is displacement and direction of the unit forces x in the directions of x1 and x2, we have to have the diagrams. Now, for the bending moments, we can find the diagram of the and the action of the unit force in the direction number upward number 1. So for the vertical part, we have even distribution of the bending moment as the force equal to 1, and the width of the diagram is 2 meters. So we have magnitude 2, and this horizontal element of the mechanical system is under the bending moment increased linearly from 0 to 2, from the end to the connection of to the point of connection of these two beams into the mechanical system. And we determine these diagrams of the bending moment on the stretched fibers of the mechanical system. Besides, we can have on the figure 3.10.3 see the diagram of the longitudinal forces. The unit force x1 do not cause the longitudinal forces in the horizontal part of the mechanical system, but in the vertical we have even distribution of the force equal to 1, as we have a unit force equal to 1. Under the action of unit force, this we need to determine the displacement, the flow case for the canonical equations as the factors in the summands. Under action of the unit force applied to the point B leftward, we have as well the bending moment diagram. So this force do not cause the bending moment in the horizontal element of the mechanical system, because this element is in the line of the action of the force, and we have linearly increased bending moment of action of the unit force in the second direction under the vertical element of the mechanical system. And as well for the longitudinal forces under action leftward of the unit force applied in the point B, we have the even distribution, because this compressed, we assume that perhaps this is with a minus sign, even distribution of the longitudinal force in the horizontal element of mechanical system when we apply the unit force leftward to the point B. And I just want to remind that the sign of the longitudinal force diagram on the vertical part of mechanical system has the sign is plus. We consider positive as a unit force x1 expands this vertical part of the mechanical system. Next, we have to find the using the Moore integral. Here we have the unit displacement. Unit displacement means the displacement under the action of the unit force. Displacement in the direction I, direction of the unit force in the direction K. So it's very usual, and we can use to determine the Moore integral. We can use Vereshchagin rule and use the diagrams of the bending moment, because to determine the canonical equations elements of the force method, we for this definite one case we have to consider the bending moment. So we can consider the superposition of the bending and the compression and the under the influence of the temperature, and the expanding this mechanical system under the influence of the temperature. But the compression expanding, we consider determining the free summands of the canonical equations. The displacement in the first direction, this is the direction upward applied in the point B, and action of unit force we can find by the product of this diagram of the bending moment by itself. So how to find that? We can first derive the rigidity of out of the brackets characteristics or rigidity of transverse section of the mechanical system, and in the brackets we have two summands for the first and the second elements of the mechanical system. The first is the area of the triangular shape linear of the bending moment on the this diagram on the horizontal element of the mechanical system, and we have the sign of plus here, y plus, hence perhaps the sign could be plus or minus, but if we product the diagram by itself, as the area the same as the ordinata under the center of area are of the same sign for the linear diagram here. So one half of 2 by 2 is the area of this triangle. The length 2, the height 2, and the area of triangle 1/2 of 2 by 2. And 2 third by 2 is maximum. The ordinate of this triangle, which corresponds to the location of the point of area of the triangle, we consider to find the area in the previous factor in the summand of the determination more integral by Vereshchagin method rule use. We have to remember that we can use the Vereshchagin method to find the Morse integral only if the diagrams are linear. At least one of two diagrams have to be linear. Okay, and the second summand is for the rectangular shape of the bending moment diagram as well. If we product the diagram by itself, we have the positive summand in the Vereshchagin rule determination of Morse integral. So we have the product of the area of this rectangular diagram is 2 the length of this part of the mechanical system by 2 is the magnitude of the bending moment and the action of the unit force in this definite one element mechanical system. And by 2 is third factor 2 is the magnitude of the magnitude in the middle of this vertical part of the mechanical system, magnitude of the bending moment diagram. Because in accordance with the Vereshchagin rule, we have to find the product of the bending moment diagram area by the magnitude of the bending moment diagram under action of the unit force. And we next can substitute all the magnitudes in the equation and find that the displacement in the first one direction and action of the unit force in the same direction is 1.67 product by 10 power to the power minus 6. The same for the 1, 2, and considering the reciprocity of the displacement in the direction 1 and direction of the force applied in direction 2 have to be equal to the displacement in the direction 2 and the action of the force applied to the direction 1. In the equality, next we have the more integral, the total of integrals by E elements of the mechanical system by 2 elements and the bending, and due to for the second one element we have 0 diagram on the action of the leftward application of the force to the horizontal part of the mechanical system. And we have only one summand remains because the bending moment diagram we have only on the vertical part of the mechanical system and the action of the force, unit force x2 to the point B leftward applied. So to find, we first consider, we have the factor of fraction 1 by divided by the characteristics of the rigidity of the vertical part of the mechanical system product by the area of the diagram. Diagram is we have this one square diagram, rectangle square diagram, and 2 by 2, and in the middle of the diagram we can find the ordinata of the second one diagram, and this is ordinata magnitude of the diagram is 1. So we have 2 by 2, and by 2 1/2 is 1. After the substitute of all magnitudes, we have that the displacements in the first direction and the action of the unit force applied in the second direction equal to displacement in the second direction and the action of unit force applied in the fourth direction equal 0.627 product by 10 by the power 2 minus 6. And the displacement and the action of the second force unit force in the direction of the second unit force the same. We have the general mathematical equation of Morse integral. We product the bending moment diagram and direction of unit force, this diagram by itself, and we have the characteristics of the rigidity as the first factor of the calculations, and we have the area of the triangular diagram as the base of the triangle, and the height of triangle we have 1/2 just area diagram, the determination, and the product by 2/3 by 2. This is the magnitude of this diagram in the point corresponded to each area of center of area. Is 2 is maximal base of this triangle, and the in the point of the area center of this diagram we have the magnitude 2 product by 2/3. And after the substitute we have that the factor in the canonic equation of force method delta log case with indexes 2 and 2 is 0 418 product by 10 to the power minus 6. Okay, and next we go to finding the free terms, and free terms are the displacement and direction of the temperature on the sides of the mechanical system. So we use previously got a formula, the last one formula. So we have to consider the areas of the bending moment diagrams and the area of the diagram longitudinal forces in the direction, in each I direction, first or maybe second I direction. And this is the area of M with index M of the bending moment diagram of the unit force, and the second area of the longitudinal force and the action of the unit force diagram. So for the force diagram, we have this bending moment diagram, and we have the unit force diagram here. In the force direction, we have to consider the areas of these diagrams. So the free term is the displacement of the mechanical system in the force direction of the point B. Force direction is the upward direction of the point B, and the action of the temperature is the factor alpha is the coefficient of linear expansion, linear temperature expansion. We have 12 product by 10 to the power minus 6, and this will be product to the brackets. And in the brackets we have the difference of the temperatures divided by the height of the section. Height is for 2 channels, number 20 is 0.2. The height meter of this section, transverse section of the beam of the mechanical system. And in the next brackets we have the total of areas of the bending moments and action of unit force in the applied in the force direction, and these areas are 2 by 2 multiplied by the divided by 2 is the area of the triangle, and the 2 by 2 by 2. So we have this area of the diagrams of the bending moment and action of the unit force in the direction number 1. And here we have the factor alpha of the coefficient of linear expansion of the material of the mechanical system and the action of the temperature we derive outside the brackets. And inside the brackets we have the difference of the temperatures. Why we have here summa total of temperatures, although in the formula we have the difference, and in the second case we have the difference. This due to the second temperature is with minus is plus 15 degrees Celsius. Second is minus. So when we add 2 plus 15 and we minus of the negative temperature minus 550 degrees, so we have plus together. And if we consider the middle temperature in the middle line of the transverse section of the beam of the mechanical system, so we have to add to the temperature on one side, the temperature on another side, and we to find the middle temperature divided by 2. But the temperature on the second side of the mechanical system, outside the mechanical system, is minus 5 degrees of Celsius. So actually we have 15 plus the negative temperature plus of minus. So we have minus 5 degrees Celsius. And this is area of the diagram of the longitudinal forces and action of the unit force in the force direction. So the force summand we have, according to the indicated formula, we have 7, after calculation, 7.32 multiplied by 10 to the power minus 3. And the same, we can find the free summand of the second canonic equation of the displacement of the mechanical system in the second direction. We use the same formula. In the second direction, we have this one. But the areas of the bending moments and the longitudinal forces we consider for the second unit force, because the second canonic equation is about the displacement in the direction of the second assigned force of the cutoff link when we do the main system out of the main statically definable system out of when we do this out of the assigned statically indefinable system. So we have first factor in the equation as the coefficient of linear temperature expansion of the material of the frame, product by square brackets, and in the brackets we have the difference of temperatures. We remember the difference of temperatures outside and inside divided by the height of the beam in the mechanical system. As the second one temperature is negative, so we have the plus sign here, and this is area of the bending moment diagram, areas 2 by the height 2 and 1/2 for the triangle, 1/2 2 by 2. And this is the temperature in the middle line of the transverse section of the mechanical system element is temperature on two sides together total divided by 2, but as the second one is negative, so we have the temperature on the one side minus 15 degrees Celsius minus, this is a plus of negative magnitude, plus of minus 5 degrees Celsius divided by 2, and the product by the area of the diagram of the longitudinal force. This one diagram is in the diagram of longitudinal force with a negative sign, as this one element mechanical system is compressed, so we have negative sign. Due to the heat of the mechanical system under the temperature T1, T2, T1 inside, T2, etc. In the middle we have the middle temperature is minus 5 plus 15. So we have 10 divided by 2, we have 5 degrees Celsius. So the middle line of this mechanical system heated. So generally, this mechanical system, due to the difference of the temperatures inside and outside, experiences the expansion, not the compression. So, but under the considered the external force of the support applied in the point B leftward in the direction x2, as we indicated on the diagram of the main system, the figure 3.10.3a. So under action of x2, this element of mechanical system is compressed. So this one, element vertical one, is under action of the forced force. X1 is expanded here, this element vertical, but the horizontal element is compressed. So we consider the science rule, and we have the minus together due to we have the negative magnitude of the area of the diagram of longitudinal force in this one part mechanical system under action of the force x2. Finally, we have a second free summand in the canonical equation of forces method equal to 2.28 multiplied by 10 to the power minus 3. When we substitute all that the free terms to the canonical equation, and when we as well specify the factors in the canonical, God factors in the canonical equations, like previously God factors in the canonical equations. And after the definite simplification, as we multiply all the canonical equation by the 10 to the power 6 to eliminate just the complex description of the factors in the canonical equations. So we have these canonical equations. After decision of the canonical equations, we have the required forces applied to the ends of the main system when we assume that we consider the compatibility of the formation doing the main system out of the statically indefinable, 2 times statically indefinable assigned system. So we, after decision of the canonical equation of the forces method like this one, we find that in the cutoff links in the point B, the force x1 and x2 equal to the God magnitudes. The God magnitudes, like indicated here, x1 is minus 5,363 Newton, and the x2 is 2,565 Newton. After that, when we have the magnitudes of the forces, x1 and x2, we can find the reaction using the balance equation, the reaction in the bending A. It's not easy, understandable, because the horizontal component of the resultant in the point A equal to minus x2 due to the balance of the considering balance of forces action in the main system, and the vertical component equal to minus x1 of the resultant applied force applied in the support A, and as well the rotating moment in the point A counterclockwise both forces. One is x2 multiplied by 2-meter arm, and x1 multiplied by 2-meter arm, the horizontal size of the mechanical system. So it's not big deal to find the other reactions remain in these reactions in the point B. But to find directions point A, after finding the reactions in the cut of links when doing the main system statically definable of the statically indefinable assigned system, this we have the forces in the cut of links. Questions and comments. First question. System of canonical equations of the forces method provided that the displacement caused by the temperature effect are symmetrical on the sides of the mechanical system as specified. The differences that in the determination of the free summands of the canonical equation of the forces method. That is the free summands equivalent to the product of the expansion temperature expansion coefficient. This summons consists of 2 parts. One part is the action of the temperature difference on the bending of mechanical system. Another one is the impact of the temperature difference on the expansion of the mechanical system. For the bending mechanical system, we consider the area of diagrams of the bending moments or under action of unit forces, but we consider the difference of the temperatures acting on other sides of mechanical system and the h of the element of mechanical system. And the second summand, the um, uh, displacement and the temperature impact on the expansion of mechanical system, not on the bending, but the expansion. That's why we consider the middle line temperature in the impact of middle line temperature in the mechanical element of mechanical system. And the area of the diagrams of the longitudinal forces and the action of unit forces on the mechanical system in the direction in which we have to find the forces due to canonical equations of the forces method. 3.8.2 temperature difference within the cross-section of an element of mechanical system as a cause of forces, system elements, and the displacements of nodes of cross-sections. The temperature difference caused the forces in systems in the mechanical system elements by the bending of the mechanical system elements. Finding linear temperature, next question, 3.10.3, finding linear temperature deformation and displacements in nodes in sections and the symmetrical influence of temperature on both sides of mechanical system element. To find the deformation, we consider the two kinds of the deformation. One is longitudinal deformation under action of the middle temperature. That is the temperature in the middle line of the transverse section of the mechanical system, assuming that the temperature distributed inside this transverse section of the mechanical system linearly. And besides, we consider the angular deformation of the mechanical system, considering the difference of the temperatures on both sides of the mechanical system. 3.10.4, reducing the formula of the Moore integral to the dependence on variable coordinate along the axis and the element of mechanical system having unequal temperature on the sides. Instead of determination of a product of diagrams of the bending moments and the action of the external load and the diagram and the action of the unit force in the direction of the third displacement for Moore integral, we consider instead of that, we consider the product of the temperature difference on the area of temperature difference divided by the h of the element of the mechanical system, the product of that fraction by the area of the diagram of the bending moment and the action of the unit force of the mechanical system. And the second summand is the product of the middle temperature of the in the transverse section of the element of mechanical system by the area of the diagram of the longitudinal force and the action of the unit force in the direction in which we have to find the displacement and action of the temperature on the mechanical system. 3.10.5, determination of reactions of supports of a double statically indefinable flat frame and asymmetric temperature influence. To find directions of support, we have to use likely the canonic equations of the force method. Using these equations, to use these equations, we have to find the factors in the summands of the canonic equations for the unknown variable subject to find and the free terms of canonic equations, which for the temperature impact depends on the difference of the temperature acting on the sides of the mechanical system and depends on the middle temperature impact for the expansion or compression of the elements of the mechanical system. Middle in the transfer section, assuming the linearly distribution of the temperature. 3.10.6 calculation of free terms of the canonical equations of the method of forces, the displacement from the temperature influences. The displacements we consider two types. First is the general expansion of the elements of the mechanical system and action of the general heat. General heat equal to middle temperature impact. So we have heated two sides of the mechanical system, and in the middle, the temperature we can find, assuming the linear distribution of the temperature inside the element mechanical system. And as well, the temperature impacts on the free terms of the mechanical system by the bending of the mechanical system due to unequal temperatures on two sides of the mechanical system. So we have to consider the difference of the temperatures on two sides of mechanical system on the bending displacements of the mechanical system. This is a free term instead of the external load as we usually consider for the mechanical systems, not under the temperature impact, but under the action of the external load. Thank you.